Okay, welcome to Distance Learning Week 3, where we move into our unit on matrices. And before I start the notes, let me just set up why we even care about matrices and what it has to do with our last unit. On our last unit, we solved systems of equations. So let's say we had something like this. We would do elimination or substitution. We would do lots of work. Insert lots of work here. And then we would have some kind of answer. If this works, someone owes me $1 million from the universe. That's probably most definitely not the solution. But we would do lots of work and we would get that answer. What a matrix is taking this system and removing the variables so that you have an easier canvas for doing your math. So if I removed all those variables and wrote this as an augmented matrix, which is something we're going to talk about on a different day, but it would look like this. 2, 3, 4. Notice those are my coefficients here. And then 8. And then on the next row, -1, -2, 6, -12, 7, 3, -8, 10. So notice what I did here is I removed the variables. I have this bar here where the equal signs were. And this is a matrix right here with the numbers and the brackets. We know that everything here represents the coefficients of the x, and that everything here represents the coefficients of the y's, and so forth. These are your z's, and these are your constants. And once we've removed the variables, we can do all the same kind of math we did before, to try and cancel things out. But this is just a sort of compact way of working. And then once you master the matrix operations for these simple ones, you can do matrices that are really large, like this represents a 3 by 3, 3 equations with 3 variables, but you can do huge matrices with dozens of variables, and that would be helpful for people in business or graphic design. Anybody who's dealing with lots of data inputs that are changing and they want to see how they work together, it's really good for that. Now we're going to do today what we're doing is just introducing you to the basic vocabulary about matrices, and then we'll do some very simple operations. We're going to add and subtract matrices. Later in the week, on the next lesson, we'll do basic multiplying by a constant, and then next week, we will talk about multiplying matrices by hand. So having said all of that, let's go ahead and do the notes. So this first bit of notes isn't doing any math, it's just introducing you to the basic vocabulary and ideas behind matrices. And these are things we'll be using these words regularly throughout the unit. So you want to get as familiar with them as you can, as quickly as you can. So the first one is just the basic word matrix. A matrix is, well, first of all, it's a series of movies with Keanu Reeves where he shows once again that he's a terrible actor, but he can be angry and fight really well. A matrix is a rectangular arrangement of numbers in rows and columns enclosed by brackets. A matrix is named with a capital letter. The size or order of the matrix is named like this: the number of rows by, that X stands for by, the number of columns. And rows go horizontally and columns run vertically. And one thing that, I don't know why this helps me because it's kind of arbitrary, but in my mind when I'm trying to remember which is rows and which was columns, I kind of write it like this. Rows go across, columns go up and down. You can also think about the columns of a building, like in architecture, like columns, they support structures, right? And they go up and down. So columns go up and down, rows go across. If we're looking at this example matrix right here, there's several pieces here that we've already talked about. One was the name. The name, if we go back up here to what we just wrote down, a matrix is named with a capital letter. So this matrix right here, its name is A. Say my name, say my name. That's what the matrix would sing if the matrix could sing. And then the size or order of the matrix, so it's rows by column. So it's the number of rows by the number of columns. So rows are horizontal. So if we're looking at this matrix, there are, this is one row, right? That's going horizontally. And this is the second row. So there are two rows. And then vertical columns, there's 1, 2, 3. So we call this a 2 by 3 matrix. One other word you might see for size or order is dimensions. So that's that three words that mean the same thing. Size, order, or dimensions of a matrix are all talking about the rows and columns. Now looking at this matrix A, how many different numbers do you see in there? 6, right? There's 1, 2, 3, 4, 5, 6. Well, those are each individual positions in that matrix. So, and what we call those is, well, you could call them position, but technically what we're going to call them is entries. So the numbers in the matrix are called entries. The entries are represented by A subscript ij. Let me show this a little bit bigger for you. So A, now notice that is a lowercase a. It's not a coincidence that the name of the matrix is A and each entry is with an A. So the name is capitalized, each entry uses a lowercase. And then this is a subscript, I, J, where I is the row that that entry is in, and J is the column that that entry is in. That's how you identify individual entries in a matrix. So going ahead with that matrix A that we just talked about. For matrix A, identify A sub 1, 2. Now this is not a 12, okay? Each of those numbers are separate from the other. This means what's the entry in matrix A that is at row 1 and column 2. So let me erase the stuff I had up here before so we can see more clearly. So you're looking for the entry that's in, oh wait, I didn't write it down. Row 1 and column 2. So here's row 1, here's column 2, and what's the entry at their intersection? It's 2. Now let's talk about the second question. A21, remember it's not A sub 21, it's A sub 2 and 1. That means row 2, column 1. So let's look at that. Row 2 is here. Column 1 is here. What number is at the intersection of those two lines? 4. So you pause the video and try the remainder 3 questions, the A22, A23, and A32. Pause it now and try that on your own. Okay, hopefully you got 5 here, 6 for A23, and I hope you had a little bit of trouble on this last one. If you did have trouble, you were thinking about it correctly. So this is asking me for the entry that's in row 3, column 2. Well, that's a problem because there isn't a row 3. There's only 2 rows. So this does not exist because there's no row 3, okay? Does not exist. So sometimes when we're so we've talked before about how to solve a system of equations, you have to have the same number of equations that you have variables. If you have 2 variables, you need 2 equations. If you have 3 variables, you need 3 equations, and so forth. So this gets us to the idea of square matrices. So here's our next vocabulary. A square matrix means probably what you think it means. A square matrix has the same number of rows and columns. So this matrix B is square, and its size is, remember, other words for size are order and dimensions. Those are all interchangeable. And so the size of this matrix B is 3 by 3 because there are 3 rows and 3 columns, and it definitely is a square matrix. And if you need something to Google today, you can go Google the song Hip to Be Square and ask your parents about it. Okay. All right, one useful concept when solving matrices is talking about the diagonal of a matrix, which is this piece right here. And the reason why that's a useful concept is this. What I just highlighted, the 10 represents an X, the 8 represents a Y, and the -1 represents a Z. And so in the future, if we're solving, if you had 1s everywhere there, it's a way of solving for each variable and knowing what the solution is. You don't have to understand that right now, but just know that's why we're talking about what a diagonal is. So diagonal entries of a matrix are the entries from the top left to the bottom right. And only square matrices have diagonals. The diagonal entries in B, matrix B, are 10, 8, and -1. So remember, only square matrices have diagonals. If you look up at this matrix on top, that was 2 by 3. It doesn't make sense to say what the diagonal is. Is it this one? Is it this one? You know, here's what I'm trying to say. The term diagonal, when we're talking about matrices, is strictly defined as just on square matrices. And it's to help when you're solving. Okay, so next page. We have these two examples here practicing all of these concepts. Given matrix M and matrix N, so we have M here and N over here. We want to talk about these questions for each of those. So go ahead and pause the video and then come back and we'll talk about M, and then I'll have you pause it again and we'll talk about matrix N. So the name of this first matrix on the left is capital M. The size is 3 by 2. Okay. Remember, the first number is your horizontal rows. So there are 3. The second number is your vertical columns. And there are 2. And element A32, again, that first number 3 is your row. So we're going to find row 3. And the second number 2 is column 2. And what entry is it where they intersect? And it's pi. Is the matrix square? Absolutely not. If yes, what are the elements of the diagonal? Well, that's not applicable. All right. So pause the video now and answer the examples for matrix N on the right. All right, hopefully you came up with this. The name of the matrix, capital N. The size of the matrix is a 2 by 2. The element at A12, that's row 1, column 2, is -2. Is the matrix square? Absolutely. If yes, what are the elements of the diagonal? So that's from the upper left to the bottom right. And the elements are 3.4 and 0. Okay, so that concludes the portion of the lesson that's just talking about concepts and vocabulary about matrices. Now we're going to talk about performing operations on matrices. And today we're just going to do addition and subtraction. So matrix addition and subtraction. A sum or difference is found by adding or subtracting corresponding entries. Matrices being added or subtracted must be the same size or order. And that's because you're adding or subtracting the numbers, the entries, that are the same position in one matrix as they are in the other. And so if they're two different sizes, you won't be able to match them correctly. And there won't be stuff to add in certain positions. So when we say corresponding entries, we mean the numbers that are in the same position in each matrix. And so again, that's why the matrices have to be the same dimensions. So if we're looking at these example matrices down here, matrices P, Q, and R, we're going to do these 3 examples here. The first one is to add matrix P to matrix R. What's the very first thing you have to check? Do they have the same dimensions? So matrix P is a 3 by 2. 3 rows, 2 columns. Matrix R is also 3 by 2. So yes, we can add those. And here's how that looks. So here's P. We're going to add it to R. And here's what that means. The first entries get added together. That's the 2 and the 3. That's row 1, column 1. Oops, sorry. And that answer is 5. And that's going to be my row 1, column 1 of my answer matrix. And then it doesn't matter which order you go in for the rest of your answers. Like if I just move to the right, to the 6 and the -2, I'm adding that, right? 6 plus -2. That answer is 4. So 6 and 2, that's row 1, column 2 on each individual matrix. That answer is going in row 1, column 2 of my answer matrix. Just like the 5 was row 1, column 1. So the rest of this problem just goes like this. 1 plus 1 goes here. And then moving to the right, 0 and 5 get added. And then the bottom row, row 3, column 1 is 1 and -4. That's -3. And then -3 and +3 at the bottom right is 0. And that's your answer matrix. So pause the video and think about adding P plus Q, how that would look. So hopefully the first thing you checked was the dimensions. So we already know P, matrix P is 3 by 2. Matrix Q is 2 by 3. And we talked about when you're adding and subtracting, the dimensions have to be exactly the same. So we cannot add and subtract these. So we can't add or subtract because of different sizes. Because they wouldn't have corresponding positions. Like if you were to just look at P and Q up here, if you were to say, okay, you know, you can find some corresponding positions, right? You can find that they both have a row 1, column 1. They both have row 2, column 2. They both have rows here. But when you go to find something to add here, row 3, column 1, there is no row 3, column 1 on matrix Q. So that's why they can't be added. That's why the dimensions have to be exactly the same for adding and subtracting. And then now we'll look at matrix R and matrix P. So we already know that they have the same dimensions because we added them in part A, but now we are subtracting them. So starting with matrix R, I've got 3, -2, 1, 5, -4, 3, minus matrix P, 2, 6, 1, 0, 1, -3. And I'm sorry about what I said about Keanu Reeves. I mean, sorry, not sorry. He's a fabulous person in real life. Okay. So row 1, column 1. In fact, you pause the video right now and you finish this problem before you come back and see my work, okay? So by far the biggest mistake students will make in this one is they'll sort of go on autopilot and just start math, 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 and thinking about other things because it's a little bit repetitive process. But right here, this is 3 minus -3. Be careful with your signs and remember that minus and negative makes positive. And so that's how we get this 6 right here. Okay, all right. That concludes your video lesson for today. Go work the practice problems and don't forget to upload a picture of it into your Google Classrooms.